Let's take a few minutes to review the key ideas from Lesson 2.1. In Lesson 2.1, we study questions related to the equations of lines or slopes of lines, and it may seem like a review and at the same time can be a little confusing. And so in calculus, what we're interested in is studying the rate of change or the behavior of a function, especially a function that's not a line. It's easy to study the behavior of a line because it's consistent. The slope is the same. Rise over run. You can see some examples here. The slope is negative. It's decreasing. It's going down, increasing. And here the slope is 0. There is no slope. It's flat. Their y values are not changing. And so why we study that, it's because in calculus, we try to simplify. We look at a function like x squared, which is a parabola. And if you look and zoom in closer and closer on it, what happens is if you analyze a piece of the graph, it starts to look like a line, like where I'm circling now. And so what we do is we simplify a function like x squared by studying the function at very close intervals that are really close together. So we're eventually, if we do that across an entire function, we can study how the function's increasing or decreasing and how fast it is. And that's what we're looking at. It's called the rate of change. And in order to do that, we just find the slope between the 2 points that we're looking at. Here's the slope of a secant line here. So here's the function, the blue graph, right? It's slowly increasing, and then here it's slowing down again, but you can see it's an increasing function, right? But it's increasing fast and then slows down. But we want to know how fast it is. That becomes a question of interest for us in calculus, how fast it's increasing or decreasing. So in order to do that, we just find the equation of the line between these 2 points, and we say that's the average rate of change, how much the y values for this function, the f of x, f of a, is changing. So this should look familiar. It's the y2 minus y1 divided by x2 minus x1, just written in function notation. That's it. That's what this is. So that's why you see this definition here of the secant of a function. M is the slope. The slope of the secant line is this equation here. And so we use that to calculate the average rate of change of a function, how much the function is increasing or decreasing. We pick 2 points and then we find the slope. Now what we do then is, and that's what you do in some of these problems, find the equation, find the slopes of the lines, and so you get through those examples there. Where this leads us to specifically, one of the most classic questions in calculus is the average rate of change. This function looks very similar to the one we had up here, just different notation. And so when we look at that, you'll see S instead of F. And in this case, F is a position. It's a location of an object. And so what we care about velocity is the rate of change of some distance. How much has your distance increased or decreased? Think of a car, miles per hour, people running meters per second or feet per second, right? You will see we measure velocity with the distance something's traveled, its position, divided by how much time has elapsed. And so that's why this notation is identical to the f of x minus f of a. Where is that? Right? But now we're just talking about velocity, and then the function is still a function, but we call it a position function. And many times we use the letter s to represent the position. And now what we do is find the average speed, how fast on average something is moving. What we care about in calculus at some point, which we learn later, is to find the instantaneous. What's the rate of change exactly at one point in time? Okay, not the average. And so that's actually kind of hard to do. And that's where calculus comes into play. All we can do is estimate here, and that's what we're doing in these first problems. And that's why these points are getting closer and closer together, because all we want to do is estimate how fast, in this case, the velocity or the object is moving, in this case, a rock. And that's why we do that calculation. And those numbers are getting closer and closer to the instantaneous rate of change, right? And that's again, why we have a different formula, because we're actually talking about velocity, but it's actually the same formula that we have here. And notice these values, which you will see, like where it's s parentheses 0.5, that number minus this comes from, you have to plug it into this equation, right? It's not 0.5 minus 0.49. You have to actually plug that value into there to get the actual position. That's the position. Where is the object at 0.5 seconds? Where is the object at 0.49 seconds? Find out how much distance is traveled over that time, and that's what that equation is here. And that's how you get your velocity with here. Now, another piece, so that's really the emphasis of many of the problems. We have something called the area problem, which we're going to focus even more on in the next sections. But the area problem in calculus is another problem we learn later, we emphasize later on. But it's interesting, in calculus, for some reason, we learned that to calculate the area underneath the function, right, is a calculus problem. And you're going to say, well, I don't get why we would do that. Well, it turns out kind of magically that when we calculate the area under a position function, for example, or sorry, of a velocity function, that the area tells us how far something travels. It's called an accumulation function. So right now we're just doing some practice problems of finding the area. It's still hard to understand why we're doing that. We emphasize that later. But these values turn out to be, and not in this case, but if it's a velocity or if it's a rate of change function, the area, for some reason, tells us a total value, how far something's traveled, how much something is worth now, depending upon the situation. And so that's what we're doing here. So hopefully that kind of, hopefully that clears up some questions you may have. Now's a good time to check in, right? And then finish your homework and then start to accumulate some questions so that when we get to further on the next few sections, you can start sending some questions on Pronto, or when you find your tutor. Again, start using the Learning Center. If you're on campus on Wednesday, you can find me. But you start to accumulate these questions, and you got to try to get some answers too. And I'll start to remind everyone to use Pronto to ask a question, but it has to be not just I'm lost. Your question should be I'm lost because of this. I've tried this, and I'm going to emphasize that a little bit as we go on.